So good afternoon all. Welcome back to the class of current electricity. Okay, I'll finish the remaining topics and we'll start with magnetism today. Is it okay? So just a second. Last time we were on some topic of reverse symmetry as far as I remember. Okay. Sorry. So this was the topic, reverse symmetry. And the question that we were discussing was this: 10, 5 and 10, 5. What was the resistance here? 10. Okay. And this was not connected, but these terminals were drawn, A and B. You know, in this kind of scenario, what is the case? Actually, it appears to be like a Wheatstone bridge. It appears to be like a Wheatstone bridge. If you draw it like this, okay, this is 10, 5 and 5, 10. The ratio is not same. So it's not a balanced Wheatstone bridge, and so it's, the principle is meaningless for us. So how to approach this kind of problem? What is the symmetry in this case? The symmetry is this. Let's say if I connect some voltage source V, let's say it supplies current I, okay? I connect a voltage source V and it supplies a current I. We already know that the equivalent resistance will always be V by I, voltage upon current. Whatever this whole system is, the equivalent resistance is given by this. So if we can find the current I, we will be able to, or if we can find V in terms of I, we will always be able to solve the question. So what sort of symmetry exists is, if I say that current branches in this manner, I1 current goes in up direction, okay, and let's say I minus I1 goes in this direction. The symmetry in this case is, they are connected in reverse order. If you see that in this case it is just like a Wheatstone bridge, but the connections are reversed, okay, ulte ho gaye. So since it is slightly symmetrical, it is not completely symmetrical, but there is some sort of symmetry. What is that symmetry? That current enters and leaves in a similar manner, because the resistances are symmetrical, even though they are reverse symmetrical, but the current then would enter and leave in same manner. If I1 current enters into 10 ohm, I1 would leave from 10 ohm, and here I minus I1 would leave. So what we are saying here, current is I minus I1, here it was I1. So out of I1 current, I minus I1 current has branched straight, has gone straight, and remaining some part goes into this. We can always find this, the remaining part, let's call it Ix. So Ix would be how much? I1 minus of I minus I1, which is what? 2I1 minus I. So current in all branches is in the form of two variables only. Okay, you have two variables I1 and I, and you have two loops. We can apply what? Kirchhoff. And we used to apply Kirchhoff not in that form which you studied. We used to apply it in some different form. क्या ये याद है आप लोगों को? हाँ? We used to mark voltages A, B, ऐसा कुछ. It was, let's say this point is A, so this would be VA. Mark it as 0. We used to do this, okay, and then we used to find what? किसी को कुछ याद नहीं है क्या? We studied a modified form of Kirchhoff current law. Do you remember? अब क्या नोट्स भी नहीं लाए हो क्या? We studied a different form of Kirchhoff law, okay, a modified form of Kirchhoff law. And for different branches we were calculating, for every junction we were calculating the total current in what manner, in some difference of voltage kind of manner, that Va minus, if this point is this is B actually, this is point B, so Vb is 0 already, so this is, let's call it C, this is D. So the current at junction C, if I say current at junction C, it would be Va minus Vc, incoming current. Incoming current is equal to outgoing current upon resistance is 10 is equal to outgoing current is Vc minus Vd upon 10 plus Vc minus 0 upon Vb is 0, right? Upon how much? 5. Okay. Again, Va is what? Is V only. If this is 0 volt, this one is V volt. The potential difference should be V volt, because if we go from this point to this point, what happens? When you jump across the battery, potential increases by plus V. Is it okay? Is it okay? So Va is actually nothing but V. So you get one equation for this junction, you will get another equation of this junction. Okay. When you get VCVD, you can find the current I1. You can find the current I minus I1. Is it okay? I'm not going to solve it, don't worry. You can try using the original NCRT wala method as well, taking loops, writing the equations for loops, or you can try this method as well. Okay, both will give you I. The ultimate purpose is to find I, okay, in terms of V, so that V up and V here cancel and we get some numeric value. Is it okay? So I will not be doing this because this is kind of an exercise for you. You have to apply Kirchhoff laws only. Okay. I will be taking a little more difficult issue actually. Somebody said what? Yeah, this is kind of a nodal thing. This is nodal thing, yes. Somebody said that is this kind of analysis is called nodal analysis, but actually it comes from what? Kirchhoff current law itself. Is it okay? It is an extension of Kirchhoff current law, but the name is nodal analysis, special name. Okay, no need of writing the name. Come on, yaar. क्या फर्क पड़ता है? मर्जी है, चलो. It's your choice. I'll be leaving this. I'll not be writing this question, solving this question for you. Okay. I'll be solving a different question, a difficult one. Can I erase this? It's not a part of reverse symmetry. Let's see who applies what sort of symmetry. This is what? A cube. Okay. Cube made up of wires. It is a cube made up of wires. Okay. And each wire has resistance R. Okay. Each wire has resistance R. Let me mark the corners. Okay. These are the corners. So, question is find R AG, R AC and R AB. RAG means the connections are made from here. Battery is connected between these 2 points. Okay. RAG means this. RAC means that the battery is connected between these 2 points, and RAB means the battery is connected between these 2 points. So here the battery is connected across body diagonal. In AC case it is across a phase diagonal, and in RAB case it is okay across side. Just a second. Now, you know this is a symmetrical figure. A cube is symmetrical, is actually a symmetrical figure. है कि नहीं है? But I don't know, I am unable to identify what kind of symmetry it is. Mirror symmetry या ये symmetry या वो symmetry कुछ है कि नहीं? नहीं इतना clearly समझ आ रहा. Because diagonal is this. ऐसे कट करेंगे तो भी दोनों पार्ट्स बिल्कुल exactly overlap नहीं करते. They are same, but orientation change करके, okay, orientation change करके थोड़ा सा exactly similar दिखते हैं. Problem है, when you cut a cube, the two parts, they are not exactly overlapping. Is it okay? So, if V voltage is supplied, this first one, out of this first one, I mean like the original current is I, but since all the paths would be symmetrical, in a cube all the parts would be symmetrical, ये आपको समझ आ रहा है? Is it really clear? Since all the parts would be symmetrical, every side would carry current how much? Now this can be understood. Okay, this much symmetry exists that actually every side would carry same current because all paths are equally good for the current to flow. You can take this path, you can take this path. Every time you have to cover 3 sides to cross the cube. Is it okay? You have to cover 3 sides to cross the cube. Now this current this one approaches D and it will further split into 2 parts. Definitely. Again 2 equal parts, I by 6. So if I keep marking these currents, the currents would be like this. I3, it splits into 2 parts here, I by 6 and I by 6. Now at C point, 2 I by 6 currents meet to form I by 3 here. So the current enters in I by 3 manner and leaves in I by 3 and I by 3 manner. You getting my point? है ना? यही हो रहा है? हाँ? So in this scenario, now since we have found the current but still it is of no use to us, we need to find what? RAG, which would be what? V upon I. Okay, using Ohm's law. So if we can find this ratio V by I, if we can express V in terms of I or I in terms of V, we'll be able to solve the question then. Okay. So let's start. Let's have one single loop because we have only one variable here. Do you see there is only one variable? Since there is only one variable, we have to take only one single loop. Okay. So in this case, since there are so many nodes, so many junctions, it would be a little difficult to use what? Kirchhoff current law in that junction form. Okay, in that extended form. It's easier to use the loop law. So let's start with the loop. Okay, this point, let's start from this point. When you jump across the battery, you get plus V. Here till here, no drop. Now let's take the path A, D, H, G. Okay, so the loop is, if we start A, D, H, G and this X and Y, X, Y, okay. We started from X, so let's start from this, write this, X, Y, A, D, H, G, again X. Okay, this is the loop. So X to Y, you got plus V. From Y to A, nothing. A to D, the resistance is R and the current flowing is R by 3. Is it okay? Resistance is R, current flowing is R by 3. So a drop of a drop of IR by 3. Why? Because current flows from higher potential to lower potential. So this must be at higher potential and this must be at lower potential. होना चाहिए ऐसा? This should be like this. Okay, so drop in potential. Again, for this DH branch, current flows from higher to lower potential, a drop in potential, again minus IR by 6. Resistance is R, current flowing is I by 6. From H to G, again IR by 3 minus IR by 3 is 0. So what you have here is a relation. If you take LCM, it is 5IR by 6. So V in terms of I, यही चाहिए था हमें. Let's find V by I. Is 5IR by 6 upon I, which is what? 5R by 6. Okay. JE asked it way back. Okay, but you know the easier exams, they do ask it. Okay. They do ask it. So shall I erase this? Can we go ahead with the next one? So we have found RAG. Let's find RAC and RAB. Is it okay? The connections are made like this. The connections are made like this. Now, is there a symmetry now this time? Do you see any symmetry? Current would not be symmetrical for sure. Current in these two branches will be same, but in third branch would be different because it has to travel a lot of distance. So what sort of symmetry? Still it's not that easy now. Even if we get two currents as same, it's not that easy. Let's tilt it slightly. Okay, let's tilt it slightly so that B and D are in front of each other. Something like this kind of arrangement. Something like this. Getting my point? Okay. You have tilted it so that you are facing the diagonal, BD diagonal. This is B point behind, D forward. So you are facing the BD diagonal. Okay. You are not facing any face. You are in middle of two faces. Is it okay? Is it okay? Now, do you see a symmetry now? Slice it. Two parts are equal. Okay. Slice it. The two parts are equal. है कि नहीं? मतलब you all look very shocked. कैसे हो गया? Is it there? I'll tell you the answer. Would you be able to solve it? Confidence? No confidence? Let's cut it. So obviously, let me mark other G and H. These are the other sides. So HD side, this DH side, it is overlapping with the mirror. No use. We used to remove this. Okay. Do you remember that when a side is overlapping with the mirror, actually the potential difference across that would be 0. The potential difference across this would be 0. We used to do this. and BF, the side behind, is also overlapping with mirror, of no use. Okay, we can short circuit them. So the first half would become this. Okay, and these are resistances, so as to differentiate between the resistances and connecting wires. I am connecting resistances this time. These are resistances and they all are short circuited, right? Mirror se cut karte the, so we used to connect all of them with connecting wires. Okay, the connection was here, and the other connection is all obviously here for first half. For second half, the same. So you can see parallel. So R by 2 in series with R is what? 3R by 2. 3R by 2, and this is also in parallel R by 2. So what we are getting? R by 2 in parallel with 3R by 2. Okay, 3R by 2 parallel with R by 2. What would be the value if I solve this? 3R by 2 into R by 2. Okay, the denominator would become 2R. Is it okay? So this is 3R by 4 upon 3R square by 4 upon 2R. You get 3R by 8. Okay, 3R by 8. So for complete, the answer would be double 3R by 4. Okay, so it is easier actually, even though it doesn't have that diagonal symmetry, but it is easier. It has some other symmetry. What if the connection is made like this? Getting my point? Okay, this cube is connected like this. Okay, there is a portion behind it. Do you see any symmetry this time? This is simplest. Bas, ho gaya. Okay. Okay, so I would not be solving this one. The connection this time was AB. Okay, between any two corners or basically across a side. Sir, so sorry, but explain again. Okay, somebody was confused. I'll explain. I'll erase this portion. Maybe it was crowded, that's why. What I'm doing is, I would try to fold it to form a corner actually. This is the problem that was to be discussed. Okay, you were initially facing this, the face. Here also there is a side, top, bottom, behind. Now you tilt it by 45 degree. You are facing this corner. So the cube should be like this. Okay, side here, one side here. Okay, now this arrangement looks like this. And if I see now, symmetry exists. If I cut it into two parts, they are exactly identical. Overlap karte hain bilkul. Okay, the mirror image would overlap with the second portion. That was the deal, na? The mirror image should overlap with the second portion. Mirror image of first should overlap with second portion. So if I cut it with a mirror, it would overlap with the second portion. But there is a problem. The problem is that this side and the side behind it, basically DH and BF, these two sides overlap with the cutting mirror. This was the cutting mirror, and these two sides are vertical, so overlapping. So basically what happens is we remove them. The resistance is not counted. Why? Because in these cases the potential here and the potential here would always be same in symmetrical cases. So the resistance is pulled out. It's of no use now. You can redraw the diagram. It's like after removing, it is like this. Because when these two are removed, plus additionally the cutting is still going on. Okay, you have two diamonds and two connecting wires, and the connections were made from here to here. Now, after you cut it into two parts, this is the resistance, this is the resistance, this is also a resistance. Okay, some confusion is there because connecting wires are also straight, and here the cube also has straight connections. So now when we connect, all the loose ends are joined by a short circuit or a connecting wire, whatever you may call it. Is it okay? Now you can solve it. This is the first half, the other half would be exactly similar. Like this. Okay. For this one also you can do the same, you can solve using the same approach. So I won't be solving, as I said. Okay, so can we continue to the next topic? Okay, you can try it at home. I'll give you the answer, just give me a second. I think it's 2/3. I think it's 2r/3 as far as I remember. Okay, so solve it. Okay, in case there is a confusion, please ask in the next class. Okay. Okay, I'll solve in the next class. ठीक है. This is a homework for you. I'll erase this one. करें आगे. Now, after all this, this all was what? Circuit analysis. Okay, so there are just two topics left. One is potentiometer. We already studied Wheatstone bridge, and you already know what is a meter bridge. Okay, meter bridge is a special case of Wheatstone bridge. Okay, so I am not solving it. I'm not teaching the meter bridge. It's very easy. It's actually basically totally Wheatstone bridge principle based and very taught very well in NCERT. I would be teaching potentiometer, and I would be teaching RC circuit. RC circuit is not a part of NCERT, but questions had been asked. Okay, what is a thermistor? A thermistor is a negative resistor. Okay, as not exactly negative resistor. It's like, you can say the temperature, it maintains its temperature to be constant. So when the temperature falls, it allows more current, it raises its temperature, and when the temperature rises, it allows less current, so that the temperature reduces. Okay, maintains its temperature. So the topic now is potentiometer. Okay, you know what is potentiometer? क्या होता है? Anyone? The basic, very simple definition of a potentiometer is, it is a voltmeter with infinite resistance. In all other voltmeters, normal voltmeters, the resistance was not infinite. What you used to do was, you used to connect voltmeter like this. Its resistance is high. Normally the voltmeters have very high resistance, but in this case you can think very easy to think that even if the resistance is very high, some current would branch. Okay, so as soon as the connection is made, let's say the current flowing was 1 ampere, and as soon as the connection is made, the current going into resistance would be somewhere 0.999 ampere. Even though there is a very small drop in current, but there would be some drop in current, and some current would come to this branch. Okay. Okay. The voltmeter needs some energy to give reading. So some current is taken by voltmeter to give some reading. Is it okay? So that means you wanted to measure the voltage accurately, but your device actually introduced an error in the reading. Is it okay? Okay, you wanted to measure accurate voltage, but your device itself introduced the error. So what's the use of this device? Okay, so potentiometer is powered by external source. That's why it doesn't need external current from the circuit. Actually, it doesn't need the current from the circuit to give you reading. Is it okay? And it will not give you the reading exact, the numeric value. It will give you something else, but you need to figure it out how to use it for reading. So voltmeter is this kind of a device. Okay, now here this is a primary battery B, which is used to power the circuit. Okay, because of this primary battery, this potentiometer will not need any power from the circuit. Okay, this is connected using these strips. The question is asked, it is very frequent, why strips, thick copper strips are used, because so that resistance is least. Okay, resistance is less and error is minimum. So this portion is the primary circuit. There is another lower part, the secondary circuit. So this is the secondary circuit. Okay, this is a meter bridge wire AB, and this is jockey J. You must have seen jockey, it's like a pin. So this portion is open because you need to connect whatever source you wanted to connect, whatever portion where you wanted to measure resistance. So before going into the detail, I'll tell you what is the principle of potentiometer, how it measures the resistance. Okay, now I have this kind of circuit. In fact, I would draw a simpler circuit. Sorry. This kind of circuit. I hope I am not writing that small today. I'm asking the online people. If it's too small, you can send a message actually. This kind of circuit, the switch is initially open. So two parts, the part 1 and the part 2 are separate, actually isolated from each other. Okay, both carry independent current. This resistance would have how much potential difference? 10 volt. Even this would have 10 volt. Now, what happens if I connect this? Would there be any change in the current? This is 10 volt and this is 10 volt. If I connect this, would there be any change in current? Hoga. If I take this point to be 0, grounded, okay, take this point to be 0 volt, then this is plus 10, this is plus 10 volt. The potential difference across both is same. So if this is 0, this is 10, this is 10, no potential difference between these two top points, no current. Okay, no current flows from here to here, same here. Okay, do you get that I have connected two parts which have same potential difference? When I connect two parts having same potential difference, no exchange of current happens. Okay, okay. The reason I just told you that actually what happens is both would have same what? Same potential. These 2 points would have same potential, no potential difference. Here no potential difference, here no potential difference. So no exchange of current in any case. Is it okay? Okay. So when two parts of a circuit are connected, yeah, two different circuits are connected in which potential difference is same, when they are connected, they are still isolated, no change of current happens. How did we use it? Let's say we connect a resistance which is a part of some other circuit where battery is connected, some other devices are connected and so on. I don't know, whatever it is. But we connect our resistance and we want to find the voltage here. Okay, we want to find the voltage here. What happens here is that the voltage in the primary circuit, if I see, if this source produces, let's say, E naught voltage, and the wire is uniform. What does uniform wire means? A wire having same thickness and same resistivity throughout. Is it okay? Okay, same material. So same thickness, same resistivity. Okay. Now E naught is the potential difference which will appear between these 2 points. I am assuming that no resistance is used by these copper strips. Is it okay? Okay. So VAB is nothing but E naught. Okay. So if L is the length, the voltage per unit length would be how much? E naught by L. We call it potential gradient. Okay. 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 Now what we do here is we use jockey. We do tap, 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 tap. A point would come at which no current flows through galvanometer. At this point, what is happening? Let's say at L length, the null point comes. Okay, no deflection comes. So at this point, the voltage VAJ will be how much? E naught by L into small l. ये ओके है कि नहीं? वोल्टेज ग्रेडियंट क्या होता है? वोल्टेज ग्रेडियंट इज वोल्टेज पर यूनिट लेंथ, वोल्टेज बाय लेंथ. सो दिस इज सेम फॉर बिग पार्ट as well as for small part. Voltage by length is voltage per unit length is same for all parts. So this is VAJ by small l as well. Okay. Okay. So voltage between this portion is this. So what we do is when we do a tap 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 kind of thing, okay, we try to find a point such that the potential difference here and here is same. When the potential difference here VAJ is same as the potential difference between resistance across resistance VR, no current will flow from here to here or from here to here. Is it okay? No current flows from potentiometer circuit to the external resistance or from resistance to the potentiometer circuit. Is it okay? Okay, we used this simple thing to build something like this. Okay, we try to find a balance point where the voltage in the upper part and the lower part are same, and at that point no current flows, no exchange of current. That's why galvanometer shows zero deflection. Now the voltage across resistance, this means is how much? Straightforward this. Okay, so potentiometer will give you the length only, rest you need to find. That's why when you were doing a potentiometer experiment in your labs, the first thing that was asked was to find the potential gradient. Why? Because you need to find this ratio. Okay, this ratio. So this is potentiometer for you. Okay, obviously there are applications, but the basic, the most general thing that could be taught is this. But actually it is nothing but an arrangement to balance voltages. An arrangement to balance voltages. External voltage and this voltage across wire are equal, no current flows, and this can be found using this formula. Is it okay? So please do it, and I'll tell the different thing as well. Okay, the other things, applications. Correct? Can we start? Now, you know the application. Okay, so I'll erase this thing only. Bas. The external portion is different. Okay, rest all are same. Rest the arrangement is same. See, in some cases, what would happen is that some resistance of these strips would be shown. There would be some resistance of these strips. Okay, so how to find VAB in that case? Current in the wire would be how much? E naught is the total voltage, R is resistance of wire, capital R, and this capital R is of strips. This may be resistance of strips or the internal resistance as well. कुछ ऐसा ही तो circuit है ये. The simplified circuit is this. There is some resistance of strips and some resistance of the wire, and some connection is made here, but right now it's open. The jockey is not connected. Is it okay? So you can find the current. The voltage VAB between these 2 points is what? I into R wire. Or you can also write it as E naught minus I into R strip. Okay, total minus the wasted voltage. So you can always find VAB even if it is not given. Okay, there in the JE questions, the resistance would always be there, even if NCRT never assumes the resistance. Okay, in JE questions it would always be there. So you can still proceed with the procedure. ठीक है, इतना मुश्किल तो नहीं है. Okay, now the application 1 is what? You know the applications. What? Comparison of EMF. This is easy. E1, E2. When E1 is connected, a balance length is found. Okay, we can say E1 would be how much? Potential gradient into L1. Potential gradient, do you remember? It is a universal thing now. Whenever you see a potentiometer experiment, try to find the potential gradient. So it would be voltage upon the length, total length. For E2, it would be potential gradient into L2. Okay, so potential gradient is a property of the potentiometer of this main circuit. Okay, it doesn't depend on whatever you connect in the secondary circuit. It doesn't depend on that. So you can find the ratio and you can compare. E1 by E2 is L1 by L2. So is it okay? Not that difficult. Right? So can I erase this? Now I'll erase this one as well and this one as well. Now the second application is what? Finding the internal resistance. Internal resistance, है ना? And the arrangement was this. You already know all this. Like this, and there is a switch as well. This is a capital R, this is small r, this is E. Okay, what initially was done? The external resistance was opened actually. This circuit was open. Only EMF was connected. We had found the balance. We had to find the balance length. Okay, we are trying to find the balance length for E only. In the first iteration, it is what? K L1. Let's say in the first iteration the length is L1, balance length. Now in the second case, when you connect this, a current circulates in this branch like this. No current enters from here or leaves from here, but a current circulates in this branch. Okay, circuit is complete. So this time if you try to find the balance point, it will show you not E but what? V. V. Okay, so let's find the V thing here first. V would be IR, you already know it. V would be IR. I is the current in this scenario, okay? Current in this loop, I. Okay, I dash keh do chahe. This is I dash. Now this thing, up this would be how much? E upon R plus R into capital R. E voltage upon total resistance. Sure? Is it okay? So this time you are balancing voltage with the remaining, with the length found in the second iteration. Okay, you are trying to find the voltage. So voltage would be KL2, where it is what? E R upon R plus small r, KL2. You can anytime take the ratio. If we take the ratio, we get E upon ER upon R plus R as L1 by L2. L1 by L2. You can find the value further, okay? You already know this. So these two are a part of NCRT. The questions are not asked directly on this. The questions are asked on the concept which I taught earlier. What you need to find is, what you need to do is, you have to balance external resistance with internal one. Straightforward. Is it okay? Okay. Balance external voltage and internal voltage. So can I give you a few questions on this? Is it okay? So the first one is, now this time you have a cell 6 volt EMF. Okay. Here another cell is connected. This is jockey A, B. Okay. You need to find balance length. This is a very simple question. Balance length. Okay. The wire has length 1 meter. Okay. And the resistance of wire you can take as 100 ohms. Okay. The balance length for EMF equal to 2 volt equal to 6 volt and 9 volt for 3 scenarios. The strips, since the resistance of strips is not given, you have to assume them to be 0. Is it okay? It's not explicitly given. So what is the potential gradient? 6 upon 1. 6 volt per meter. And you already know that any voltage in the secondary portion, is what? Somebody is asking a doubt. What is the length of potentiometer and why? Length of potentiometer, it is the length of the wire actually, potentiometer wire. Okay? And you need decent enough length. So that there is, if we have small wire, potential gradient would be high. Okay? Which means what? For very small change in length, the voltage would change from through very large values. छोटा वायर रखने में नहीं, रेजिस्टेंस तो कम रहेगा. छोटा वायर रखने पे क्या होगा, हाँ पोटेंशियल ग्रेडियंट ज्यादा होगा ना, लेंथ कम हुआ तो potential gradient would be more. Okay, so even very small change in length would cause large change in voltage. Sensitivity would be low. Okay, sensitivity would be low. So we need long wire so that there is, less change for, small change in length, there is less change in voltage. Is it okay? Is there someone else? और कोई नहीं है? So for any voltage connected on the secondary side, you need, you can write this formula, KL, straightforward. So this is 2, this is 6, this is L. L would be 1 by 3 meter. For second case, L would be 1 meter, but what about the third case? This is L1. L2 would be 1 meter. L3 क्या आएगा? If you solve it is 1.5 meter. You have 1.5, you have 1 meter long potentiometer wire, but the balance length is coming out to be 1.5. How can it be possible? How can it be possible? नहीं हो सकता. The problem here is you can never connect a, a secondary cell. हाँ हाँ नहीं, comparable भी नहीं होना चाहिए. The E thing here, okay, EMF or voltage which you want to measure should be always less than VAB, voltage across this wire, which is generally less than the EMF of cell also, cell itself, the main cell, okay, the battery. Is it okay? So the problem with this is that you have connected a cell of higher voltage than the main battery or the primary battery itself. Is it okay? Can I erase this? Can I erase this? So this was easier. This one was easier. Let's do another one. Okay, this time the potentiometer wire has length 6 meters. Okay, the potentiometer wire has length 6 meters. Somebody has asked, what is the difference? You are not listening when I was saying, when I was explaining the difference. I said voltmeter is, potentiometer is a perfect voltmeter. It is an error-free voltmeter. Okay, okay. A normal voltmeter measures voltage while drawing some current from the system. It will not take any current and still give you accurate reading. So there is no other difference actually. Okay, both measure voltage, but it measures accurately. So in this scenario, what is happening? E is EMF of the cell. Okay, R is its internal resistance. The wire has resistance 14 R. Length is 6 m. You need to find balance length for E by 2. And I'm expecting answers from online people as well. Online पता नहीं क्या होता है, कभी कभी sometimes people answer but sometimes they don't. Let's see. Now, check. Dekho, it's not that difficult. Let us assume that the balance point is established. When balance point is established, no current here, no current here. Okay, the only current circulates in this circuit. Can we find the current? Yes, we can find the current. Total resistance is 14 R here, R here. Okay, so the total resistance would be 15 R. Okay, current would be E upon 15 R. Okay, so voltage across AB portion. AB is a resistance of 14 R value. Okay, so VAB would be I into R wire, which is E by 15 R into 14 R. So 14 E by 15. This is VAB. Potential gradient would be 14 E by 15 into 6. Okay. Now for this, E by 2 is equal to K into L, which is what? 14 E by 15 into 6. ठीक है. E by 2. Okay. You can find the answer. Hmm? 14 E तो कट जाएगा है ना. This is 3 45 sorry नहीं 45 upon 14 meter. Okay, this is just over 3 meters है ना. 14 3 is 42 से देख सकते हो. just over 3 meters. ठीक है. So I'll erase this. Let's start with the next topic. Anyone you are writing? Can I erase? I'll start from this side. Now, this is RC circuit. What is RC circuit? Resistance and capacitance connected. Okay. A capacitance and a resistance. We have two cases actually. I'll first write the cases. First one is growth of current. Growth of current, how does this happen? Connection is made at t equal to 0. At t equal to 0, connection is made. So current starts flowing from battery. Okay, capacitor is initially uncharged. Capacitor is initially uncharged. So what happens? Current, charge starts flowing from battery and starts depositing on capacitor. So positive charge flows from here to here. Here what happens is negative charge flows from here to here. Okay, this happens till the time when capacitor gets fully charged. After which nothing would happen. The capacitor would behave like an open circuit. So we are studying the current that would flow through the circuit when the capacitor was charging. Okay, before it was fully charged. Okay. Now at t time, let's write the values. At t time, what happens? Let's say the charge on the capacitor plates is Q. Okay, this is plus, this is minus. The current flowing is I. Current flowing is I at t time. At t time, let charge on capacitor be Q and current be I. Okay. So by Kirchhoff voltage law, let's start from this point, starting point x. यहाँ से जाते हो, if E is the EMF, यहाँ से जाते हो, okay, यहाँ से ऐसे जा रहे हो, x से, so the first thing you get is a cell, change in voltage plus E, change in potential plus E, from here to here nothing, from here to here, decrease in potential, okay, plus to minus, so this is minus Q by C. Do you remember voltage across capacitor was Q by C? And for resistance, the current is flowing like this. So this is plus, this is minus. Current flows from positive to negative potential. So minus IR is equal to 0. Okay? Now IR is equal to E minus Q by C. I is what? dQ by dt into R. Okay, even R I am trying to bring down. E by R minus Q by C. Okay. Okay. Now, in fact, no, don't do this. Do this. E minus Q. This is RC. Take LCM and bring it here. Okay. CE hoga. You take LCM. Okay, the LCM would be CE, okay, total thing would be CE minus Q upon C, bring C there. So now do this, dQ by CE minus Q is equal to dt by CR and integrate it. Initially the charge was 0, finally it would be some value Q. Initially the time was 0, finally it is T. इसको कैसे integrate करते हैं? This is of the form x upon a minus x, dx upon a minus x. How do you integrate it? Yes, exactly. नहीं. This is simple, very simple. Minus CE minus Q with limits. I will not write it here. भीड़ हो गई है बहुत ज़्यादा. Okay. This is minus ln CE minus Q. Why minus? Because coefficient of Q is negative. Okay. And limit 0 to Q is equal to dt. dt का t हो जाएगा, sorry. T upon CR 0 to T. ठीक है? Okay. So taking the negative side on the RHS, so you get ln C minus Q minus ln CE is equal to minus T by CR. ये हुआ? CE क्या होगा? When the capacitor is fully charged. Capacitor fully charged कब होगा? जब voltage here and voltage here are same or potential difference across capacitor and battery is same. Okay, then capacitor is fully charged. So at that point of time the charge would be how much? The final charge would be CE. Final voltage of capacitor would be E. So final charge would be CE. So we can replace it as capital Q. Okay, so this thing using the property of log capital Q minus Q upon capital Q is minus T by CR. Can I take ln on the other side? It would be 1 minus small q by Q is equal to, or you can write this, Q minus Q upon small q is e raised to r T by CR. Okay, you can find the charge the charge would be q1 minus e raised to power minus t by cr. Okay, I hope it's all clear, still clear, nothing is crowded. Okay, this is the charge, this is the charge. If I could erase the top portion, ये तो erase कर लूँ. This is the charge. If I draw a graph for the charge q t, you can check as as time increases, this e wala factor will decrease. When t is 0, e raised to power 0 is 1, right? You can check when t is 0, e raised to power minus 0 is 1 actually. है ना? As t increases, because power है negative, the power is negative, this thing would be actually something like this, q1 minus 1 by e raised to t by cr. So as t increases, denominator increases, this total thing would decrease and charge would increase. Okay, so if this is the charge, the graph rises like this. Okay, okay, rising exponential graph. Okay, but with a negative power. कुछ ऐसा होगा. You want to find current, use this dq by dt. Okay, the current would be how much? If you solve it completely, you get e by r e raised to minus t by cr. Okay, if you solve it, I have done it for you because time is short. T. Now, if you check this, E by R is the starting current. You know, initially the capacitor was not obstructing the flow of current. Initially the capacitor was allowing current to go through fully. So the initial current was E upon R only. Okay, initial current was E upon R. After this, as t increases, this thing will go in denominator. Power negative hai. The power is negative, so this thing will go in denominator. It will be actually E by R e raised to power t by cr. As t increases, current will decrease and it will become 0 at infinite time. When t becomes infinite, denominator becomes infinite, current becomes 0. So this is I naught equal to E by R, maximum current, then it drops and meets at infinity, meets the x-axis at infinity. Can we start? Okay. Now these relations, they give the value. A capacitor takes infinite time to charge completely. Okay, but still it will charge to a very high value in less time. This value C by CR actually, this value is called tau. You know, remember tau symbol for torque, same symbol actually. Okay, relaxation time में भी यही तो use करते थे, है ना? Tau is CR. Okay, this is a constant. Okay, growth constant you can call it. Growth constant. Okay, when time is equal to, why is it this important? When time is equal to tau equal to CR, what happens is the charge becomes q into 1 minus 1 by e, ये हो जाता है। इसमें देख सकते हो आप t की वैल्यू cr के इक्वल कर दो 1 by e, दिस इज नथिंग बट 0.63 कैपिटल Q। ओके, सो कितना क्या होता है ये ग्रोथ कांस्टेंट इज अ टाइम। ओके, इट इज अ टाइम, राइट, इट इज अ टाइम। सो द डायमेंशंस ऑफ CR वुड बी दोज ऑफ टाइम एंड यूनिट वुड बी सेकेंड्स। इज इट ओके? कैपेसिटर और रेजिस्टर का प्रोडक्ट इज टाइम। So this is the time in which a capacitor charges to 63% of its maximum charge. Okay, तो इस हिसाब से करंट के साथ क्या होता, करंट 0.37 हो जाता, चार्ज 63% इंक्रीज हुआ, so the current would decrease by 63% and it would remain at 37%. अच्छा, somebody is asking, please explain the graph again. I don't know which one, so I have to explain both the graphs. In this graph, if you pay attention to the charge, in this graph, if you pay attention to the formula for charge, e raised to power minus t by CR it was there. This was negative sign, power mein, which means it could be written like this. Okay, e raised to power t by CR in denominator. ठीक है? Now, since as time increases, initially the time when time was 0, this would be 0. When t is 0, e raised to power 0 is what, 1. So the thing becomes 1 minus 1 is 0. Okay. So as t increases, this denominator increases. Okay, total value decreases and the difference increases. Okay, when t becomes infinite, so denominator becomes infinite, this value becomes 0, the difference becomes 1. So the charge increases exponentially, but it rises rapidly in the initial parts, then slowly in the later parts. Okay. For the current, the graph is reverse. Since you can see it on your own, charge is rising rapidly. Do you remember? I is dq by dt. So can I say current is slope of charge time graph, slope of qt graph? You can see the slope is high here, then less, then less, then less, and finally becomes 0. You can plot the slope, it comes out to be this. The value of I is high here, then less, then finally becomes 0 after infinite amount of time. Is it okay? Now, second part is decay of current. Decay means the current is reducing. The capacitor was fully charged initially. Okay, this was fully charged up to what? EMF E. So the charge here was CE. Charge here was CE. Okay, when you connect, what is meant by growth constant? See, growth constant is time. It is actually time after which the charge becomes 63% of the maximum value. You can also say it is the time after which current drops to its 37% of its maximum value. Okay, or initial value. Okay. So current drops to 37% of its initial value. So a circuit having high charge constant, growth constant. A circuit having large growth constant will charge slowly. जिसका growth constant ज़्यादा होगा, it will charge slowly. And if someone has growth constant less, it will charge rapidly. Is it okay? So we try to make this kind of arrangement in our scenarios, that in most of the cases, in most of the electronic circuits, we try to keep the growth constant to be small, so that charging and discharging happens rapidly. In case of electronic equipments, they are very high speed equipments. All instruments are high speed. So you don't want to waste time in charging and discharging, right? and capacitors are used even in TVs also, even in TVs. So decay of capacitor, this is fully charged. Initial charge was Q equal to CE. Can you please explain growth constant once again? Okay. I'll draw a table. At t equal to 0, the charge was 0. Okay. The current was E by R, which is the maximum value. Okay. When a time equal to growth constant is passed, when a time equal to growth constant passes, charge becomes 63% of Q naught, current reduces to 37% of I naught. This is the maximum current. When in 2t, 2 tau passes, then you can calculate e raised to power something square would be there. So when time becomes infinite, charge becomes maximum, but current drops to 0. So everything in a single table. Okay. Okay. Okay, can I erase this? Now, in case of discharging, when you connect this, initially what happens? The charge flows rapidly. Initially, the charge flows rapidly and then it reduces and then reduces, because as the capacitor gets discharged, okay, less and less charge would go. Somebody is asking KVPY exam is there tomorrow or something. Okay. So I'll explain whatever I was explaining. Sorry, I got distracted. The question here is, the point here is, as the charge gets, as the charge reduces, less and less charge would move from capacitor plates. Tendency kam ho jayegi na, there would be less tendency of, pushing the charge. When the connection is made, everything is has just started. It has maximum voltage. Maximum voltage means it would supply maximum energy to charge to just run. So the charge would run and cover the whole cycle completely. Okay, positive charge and negative charge. But in case of, but as the charge reduces, the voltage across capacitor would reduce. Okay, okay. So less and less charge would go, and less current would also flow. Okay, okay. We can always go via the KVL method. I'll write the KVL equation. The KVL equation says, let's start from this point. The current is flowing like this. Okay, you start from this point, let's go this way. Okay, let's go this way. You are crossing it from positive to negative direction. So you write negative IR, then you are crossing it from negative to positive direction. So you write plus what? Q by C is 0. Can I write IR is equal to Q by C? I would write dQ by dt into R is equal to Q by C. No, there is something wrong. The point here is, charge is decreasing. Current is a positive quantity, right? dQ by dt, if you draw the graph, charge would be reducing. So dQ by dt is what? Slope of this curve. Slope of this curve is negative, but current is a positive quantity. We place a negative sign here for this scenario. Getting my point? Getting my point? Okay. What is happening is, charge is reducing. Okay, charge is decreasing. So dQ by dt will give us a negative value. but current is positive. So to make it positive, we place another negative sign. Two negatives make a positive, right? Okay, so now you can solve. Okay, again you can see that it would be dq by q is equal to minus dt by rc. You can integrate it and so on. I'll just write the results. Q is q naught, where q naught was ce. Okay, e raised to minus t by rc. Current is I is equal to I naught e raised to minus t by rc. Okay, ठीक है? You can draw the graph. Since both have similar functions, the graph for both would be this. The charge initially is q naught and it decreases. The current initially is I naught and it decreases. Okay, the graph would be same. Okay, a question was asked some time back. In that question, there was not a single capacitor. There was a group actually, 2 or 3 capacitors in parallel series arrangement. Okay, in that kind of question, let's say if we have, this topic is complete, but let's say if we have this kind of arrangement. These all are connected using a resistor and a battery. The question is asking what would be the current through the battery, or the resistance. So what do you need to do? Combine all of them, form a single capacitor. Okay, let this if these are C, these two will parallel, they would add to form 2C in series with C. So 2C into C upon 2C plus C, it would be 2C by 3. So the equivalent capacitance is 2C by 3. The growth constant would be how much? 2C by 3 into R. Just replace C with equivalent capacitance. Is it okay? The same thing can happen in equivalent resistance as well. Is it okay? Same thing can happen in equivalent resistance as well. Okay, so I'll erase this. Now let's start the topic which we were supposed to start today, and somebody is asking. People are so confused these days. See, growth constant, I'll write it. Growth constant is that time in which charge increases to 63% of its maximum value. Okay? Or you can write growth constant is that time in which current reduces to 37% of its initial, which is also the maximum value. Okay. So it is very difficult to digest that actually something which has a formula of this type, capacitance into resistance, can have very simple units like time. It is very difficult to digest. So acknowledged, I hope now this time it is clear. We don't have a very good definition. The only definition is this available. For decay, we said this was the arrangement. Okay, the capacitor was fully charged. So the voltage here was the charge here was CE. Okay, E EMF की बैटरी से पहले कनेक्ट किया गया था. Okay, it was connected to a battery of EMF E earlier, so it would be having a voltage E and charge CE. Is it okay? Now when the connection is made, what happens? If I take KVL, the current flows from, let's say this is positive terminal, this is negative terminal, the current flows from this to this direction. This is positive sign, this is negative sign. Okay, let's say you start from this point, you move in an anti-clockwise direction from this point to upward, then here, okay. So if you are moving like this, you start, you know, the resistance has positive and negative terminals in your direction. Okay, you start from positive to negative side, so there will be drop in potential. Is it okay? And from here to here, there will be rise in potential. So plus how much? Q by C is 0. I can write IR as Q by C. I can write R into, this is dQ by dt, is Q by C. Now there is a problem. We need a negative sign, and I just told you. Why do we need a negative sign? Yeah. The thing is that actually charge is decreasing. Charge is decreasing. Okay. So when charge is decreasing, the rate of change would be negative. This is what? Rate of change of charge, rate of flow of charge. It is a negative quantity because Q is decreasing, so dQ by dt would be a negative quantity. And if dQ by dt is a negative quantity, current would be negative. If I take current as dQ by dt, since this thing is negative, current would be negative. Okay, which is impossible in this case because we took very clear, you know, in normal cases, current negative means that we have taken wrong directions. But in this case, we took right directions and still the current is negative, which actually is the issue because charge is decreasing. Charge is decreasing. Okay, so to make current positive, we place a negative sign. We make two negatives as one positive. Is it okay? This is negative and even dQ by dt is negative. So two negatives make a positive. Is it okay? Now you can solve this. dQ by Q will be minus dt by RC. Integrated. Initially the charge was Q. Complete charge tha. Finally it is not 0 actually. We are discussing about some middle time, okay, not final time. Okay, finally it is Q. Time is 0, this is T, you can integrate it. Some function of log would come, you can integrate it. Okay, so the charge would come out to be Q e raised to minus T by RC. If you differentiate it, the current would come out to be I naught e raised to minus T by RC, where I naught is what? I naught is E by R, initial current. Okay, I cannot explain how to differentiate actually, that you need to learn on your own. This is maths. All this was maths. Only this was physics till this point, forming the equation. Rest all is maths. You need to learn maths first then. So, can we wind this up? Can we wind this up? Is it okay? No, I'm not winding the class actually. I'm winding this, the topic. Okay, let's start with the next one. No, this was magnetic effects of current. You already know that this guy Orested accidentally discovered that actually there is magnetism involved with flow of charge as well. I'll not be detailing that, you already know the kahani, the story. So let's come to the point. The first important topic would be what? Biot-Savart law. Okay. What does this say? it says that, let's say this is a wire, we have small segment, okay, of length dl. So this has length dl. We define a vector dl vector here. So I would be writing it as dl vector actually. The length is dl, but I define a vector dl vector whose magnitude is equal to the length of segment and whose direction is along current. Okay, since current is a scalar, we cannot use it as a vector. It is a scalar and has a direction. So we define another vector which uses the direction of current. Okay, so it says that if P is a point, okay, taking this as origin, you take this as origin, taking this as origin, if this is the position vector of P point, this law says that the magnetic field due to this small element would be mu naught upon 4 pi r cross I dl sorry, ideal cross r hota hai, I was writing it in reverse order, upon r cube, okay, where small r is what? Distance between that element and this point. ठीक है? And you already know this thing can be written as ideal sine theta upon r square. Direction would be r cap. Direction of cross product would be n cap, sorry. Is it okay? The direction can be found using what? Direction of n cap can be found using right hand thumb rule. This you already know. Okay? Okay, I'm rushing through all this because you already know this. The only point was dl vector. Why do we need dl vector? Why dl vector is used? Length is a scalar. But the problem is we cannot take current as a vector. Current is a scalar for sure. Just like we used area as a vector, area is a scalar, right? We used area vector for our convenience. We here also defined length vector. Okay. So can I erase this? Now straight away we come to its applications. So by the way, this Biot-Savart law is actually valid for small element. Okay, if you want to find the magnetic field due to a larger element, what you need to do is you need to use superposition principle. Do you remember superposition principle? If there are several small elements, this one has distance r1, the field due to this one would be dv1, field due to next element would be dv2, field due to third element would be dv3. So you need to add them vectorially. Is it okay? Vectorially. To find the net field, you need to add them vectorially. We studied this in electrostatics, I guess. We studied this. So magnetic effects of current. Now, first application Biot-Savart law ka. First one is B due to a straight wire. I am not saying long here. Long would be a special case of this. This is a wire. Length is limited. You have a point P here. The perpendicular distance is r. Let's say it is carrying current I. Is there, okay, sorry. I thought somebody is asking some doubt. So, in this scenario, what we need to do, we had already seen this kind of construction in which case? Do you remember? In electric field also we studied this kind of scenario. We assumed a small element at a distance x, okay, a small element dx. And we try to find the field due to this element, है ना? this is, let's call it A. The perpendicular distance is A. Okay, the perpendicular distance is A because R is this thing. R is this thing. Okay, and slightly. This is R. Let's say if the angle is theta, this small element has angle d theta. You know what? Okay, I overshot. It's okay. The class will be continued. I'll continue these things in the next class. I forgot the track of time. Sorry.